Hello, welcome to our third lesson on C++ from Python. This lesson's going to be a bit of a grab bag. We're going to cover a lot of different topics, but some important details will be left out of each of them. We will cover enough that you can start to use these features of the language, but in future lessons, hopefully we can come back and teach you some more of these details that we left out, go into each of these in a bit more depth. First, however, let's review the homework. Hopefully you read carefully and you implemented using a double instead of an int. It's not a big deal, but technically it's wrong if you don't follow a spec. Second, string comparison should just work. You should just be able to read an input into a string and test if it is equal to other strings, as we do here. And hopefully you had code within your main that looked something like this. It doesn't have to be exactly the same. Now, the first new concept we're going to learn is the difference between declaration and definition. I mentioned before that you always have to introduce a function before you can use it. Now, I'm going to be more precise in what that means. In order to write code that uses a function, C++ needs to know that the function you're using exists. It needs to know what type it has, what inputs it accepts, what type it returns. But C++ doesn't need to know the full definition until the very end. So if we just want to introduce a function, that's called a declaration. Here's an example with the function one more. If you look down below, you'll see that the definition is it returns one more than whatever number you give it. So 1 more of 3 is 4. But we haven't defined it yet. We're just introducing it returns an integer, its name is 1 more, it takes 1 integer argument. But there's no body. Where we would have started with an open curly brace, instead we say semicolon, we're done. I'll tell you more about this function later if you need it. So this is a declaration. It lets C++ know that such a function should exist. And it then allows us to write other code that makes use of that function. If we didn't have the declaration, this would be invalid. But since the declaration is there, C++ understands how to interpret our meaning and knows that this should generate code for the computer that calls whatever that function is once, and then take what it gets, calls it again, and returns that number. Finally, we can come back later and write our definition. So to recall, the two words here are declaration and definition. A declaration introduces the function's type, and, well, technically its name. The definition tells C++ all the details. And the declaration must appear before the function is used. The definition can appear anywhere, before or after. Another new topic, structs. If you've used the class keyword in Python already, struct in C++ is quite similar. Some small differences in syntax, but it's very close. A struct allows you to define a new type that lets you group together several different pieces of data. Now, in Python, these several different pieces of data were referred to as attributes. In C++, we usually use the word member. We also sometimes use the word field, but I strongly prefer we, as much as possible, stick to the word member. I'll also mention that there is a notion of struct that was in C before even C++, which is a bit more restrictive. It doesn't do quite as much. We're only going to focus on it from the C++ perspective. So here we define a struct. You start with the keyword struct, followed by the name of the struct, and then curly braces, followed by a semicolon, delimit everything that goes inside. Again, this is the same pattern in C++. Instead of using spaces and indentation, we're using curly braces to represent the body of the definition. And then we can define variables within the struct, just like we would within a function. Every instance of this struct, every time I make a variable of type full name, it is going to own its own first name and last name that have type string. These are the members of the struct. I could declare a function greet that takes a full name as a parameter. I could define a local variable in main. The variable is name, and it has type full name. And just like in Python, in order to refer to members of name, or attributes in Python terminology, I just use a dot. The variable name dot the member name. And since name.first is a string, name.last is a string, I can read them from cin just like I would any other name. And then I can use that variable name and pass it to a function that expects a full name. And down here, I can also read from those members the same way, using the dot. Now, one of the things that's cool, and this is again something you could already do in Python, is you can define a member function. First and last are member variables. They store data. Bond-like, however, is a member function. It's like a verb that's special that belongs to full name. So here, bond-like is a member function. Sometimes we also use the word method, but it is a member function that returns a string. It's the name the way James Bond would say it, or specifically the way James Bond would introduce himself. If you're not familiar, James Bond is a character who is a spy in a series of movies who always introduces himself as Bond, James Bond. So we can construct to that same string. If first name was James, last name was Bond, this would be Bond plus a comma and a space, James, space, Bond. It's just a cute little example of a member function. Notice that we can refer directly to the variables, the member variables, first and last within this function. Because this function, it's kind of like it belongs to the class, it is allowed to see and use freely the variables that are defined here. One difference from Python is you don't need a self keyword here. If you had written the equivalent code to this in Python, there would be an additional parameter, self, and in order to refer to last and first, I would type self.last, self.first. That's not required in C++. There is an equivalent keyword, this. It is literally the word this. But we'll get into that in more detail later. We don't need it at first. Now, I introduced declaration versus definition. We've started talking about structs. We can do the same declaration versus definition distinction with member functions. Here now, the bond-like member function does not have a function body. It ends with a semicolon. This makes it a declaration. This allows us to put the definition outside the struct later on. But I can't just define a function called bond-like that returns a string. I have to make it clear to C++ that I'm defining the function bond-like that belongs to the struct full name. The way I do that is by putting the struct name and then colon colon. Colon colon is very similar to the dot. It means full name colon colon bond-like is interpreted as the bond-like that is within full name. For now, just know that sometimes you have to use a dot, sometimes you have to use a colon colon, and I'll leave it at that for a while. I do want to mention, though, that this is the way C++ libraries are typically organized. Whenever I write a library, whenever anybody writes a library, typically we write two or more, but at least two files, one of which has only declarations. The other file has the full definition. And the way C++ programs are built, this allows the declarations to be shown to your code so that you can use the library, so that C++ knows what functions should be available. But it's convenient, for details again that we'll get into later, to have all the definitions be separate when we can. Now, there's another special kind of function, member function, we should talk about. It's the constructor. This is a special member function that you use to create instances of your new type, of your struct. Again, in Python, the name of a constructor is underscore underscore init underscore underscore. In Python, we use a special member name for the constructor. In C++, it's a little different. We just use the name of the struct. Much like in Python, we can take parameters. And then we can have a function body that is the recipe to follow every time we use this to create an instance. Now I'm going to point out that notice there's no return type here. It just goes straight into the name. Full name is the name of the struct. Now the reason it's this way in the syntax is it's almost like the name, full name, of the constructor and the return type, full name, are the same. So it's just when they were coming up with the language, they decided, you know what, we won't write a return type because the return type always has to be the same. So rather than make you type full name, you just have to type it once. And constructors are a little bit special for other reasons anyway. We take two parameters, FST, LST, which are short for first and last. I intentionally just made them slightly different spellings of kind of the same thing. We assign them to our member variables, and then we're done. In order to use a constructor like this, we will mostly use this. It starts out like a variable definition. We start with the type of the variable, the name of the variable, but then we can do parentheses, and inside it's almost like we're calling a function, and we pass the parameters that go to the constructor. There's another way we can do it, which has some subtle differences, but some people prefer. I would rather you just stick with the first, but I just want you to see this. We can also do full name, name2, this is a different variable, is equal to, and then we can use the constructor almost like a function that builds a full name. This part of the syntax where we use the constructor like a function, this is useful, and we will do this from time to time, though the full line is not the best example. Now, this is a really big topic, values and references. You may recall from Python that there's a difference between value semantics and reference semantics. And that difference is whether or not a variable can be modified when you pass it into a function. In Python, this depends on the type. In the first example, well, let's first look at what this is. I have a function that takes two parameters, and it says the first is incremented by the second. If I call this function with ints, because plus equal has, or rather because the ints have value semantics, when I pass an int to a function as an argument, that function gets a copy of the value. So when the function plus equal does the variable x plus equals the variable y, x started at 1, y started at 1, x is now 2, it only incremented its own copy of the value. So at this point, when I print out a, it's still 1. Lists, however, now I'm going to do the same thing where a is a list containing 1, b is a list containing 2. When I call the plus equal function, the list x will be incremented by the list y. Plus on lists will concatenate lists. And now it will actually print out the list 1, 2. It changed a. Whether or not a value can be, or a variable can be modified depends in Python on its type. Simple scalar types like int, bool, float are not modified because they're always passed by value. On the other hand, types like list or dict or classes that you define are always passed by reference. They can be modified. Now, they might not be modified depending on how they're used, but the function is allowed to modify them because it refers back to the same instance. A reference means I don't just have a copy of your value, I refer to your value. And so if I change the value I refer to, I change the value you have. Well, a great power of C++ is that you get to choose. C++ allows both value and reference semantics for basic types and class types, or struct types. Here we do kind of a similar thing. A function add1 takes an integer x, it increments it by 1, and if you're following closely, you might realize that this function does nothing. Because it increments its own copy of x, it doesn't return anything, so this add1 will not accomplish anything. In main, I initialize x to 4. I call add1. I print it out, and this will print a 4. However, by adding this ampersand character, I state that x is a reference. Any variable passed to add1ref, I will not pass its value. I will pass something that allows to add1ref to refer to whatever variable was used as the argument. When x is incremented by 1 here, it refers back to this x. So, well, let me go to the right line. Add1ref here, because I'm passing in this x, and it is a reference, it refers to this x. When it does its increment, it actually changes the value and it prints 5. So what's so great about this, again, is you get to choose. In Python, you can't pass an int by reference. You can only pass it by value. In Python, you can't pass a list by value. If you want to guarantee you have a small list, you don't care that you're going to waste time making a copy, you just want to guarantee that the function you're calling won't modify it, then you actually have to go out of your way and copy it ahead of time to pass it to that function. In C++, You get to choose. There's another detail that helps out called constants. Const, which is the actual keyword we use for constant in C++, is a promise that something will not be changed. This is not a super practical example, but it's an example of using the keyword const. When I use a const on a parameter, I promise that I won't change that parameter. That's useful combined with a reference because it promises that even though I have access to your instance of the variable, I promise I won't change it. There's a very good reason we might want to do this. It's rare that we would do this for an int, but when we start using classes, it's very valuable. There's another example here. This code is invalid because const, recall, is a promise that we won't modify x. But within the function body, we modify x. The compiler will reject this when we try to build our program. We'll never even have a program to run. It'll say, no, 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 you said you weren't going to modify x, and then you went and modified it. That's not okay. We can use const with structs as well. If we want to, we can take a member function and annotate it with the const keyword at the end as a promise that this member function will not modify point. It never changes the members. One other example that I should have included, it's possible to just declare a local variable const. If I wanted to have a const integer variable, I might do const int x equals 1. And then the compiler will prevent me from ever changing it. You might wonder why it would be useful to have tools that take power away from you, where you promise not to do a thing. Well, why wouldn't you just not do the bad thing in the first place? The reason is it helps us reason about our programs being correct. I know that I make mistakes. The larger my program is, the easier it is to make mistakes. If I can write const in a few places, actually I try to write const in as many places as I can, when I'm looking at some code where I pass a reference to my very important data to a function, if I can just see that that's annotated as a const reference, I don't need to read the whole function to be reminded, oh, that's okay, it's never going to modify my very precious data. I just have to see the const keyword, and I know then that the C++ language will make sure that I don't make that mistake. A pretty big change here. We're going to switch to reading from files. The good news is that reading from files in C++ is very, very simple. A tiny bit of history for why. C++ kind of follows from the language C, and C is a programming language that was invented, we'll say, alongside the operating system Unix. And a key feature of Unix is that pretty much everything is a file. Now, this sounds weird at first, but the terminal that you print to your program is actually a file. In a sense, the keyboard that you get input from is a file. Now, they're not complete files. The screen is a file that you're allowed to write to, but not read from. The keyboard is kind of like a file that you can read from slowly, but not write to. But because that's the underlying model, the good news for us is that to read from a file instead of read from the keyboard, we can use almost the same code. Normally, to read from the keyboard, we use cin, a special object that's defined in the iostream library. If instead we include the fstream library, that gives us access to the ifstream class, which is short for input file stream. It allows us to create objects that are like cin, but they read from a file. And if you recall from before, input then is the name of the object, and it's calling a constructor. So this is the parameter. We pass in the name of the file to read, and from then on, the input object works like cin. We can use it with the stream operators and read from it the same way we would read from the keyboard. Writing to a file is actually almost the same. If we wanted to write to a file, instead of std ifstream, we would do ofstream, which is unsurprisingly for output file stream. There's a bit of new syntax here, and I'm mostly going to brush over it. Vector is the type in C++ that is closest to Python's list. There are actually a lot of different ways that we could write something like a list in C++, but a really good default in that it's pretty easy to use, not particularly dangerous. There are very dangerous ways that you could try to write C++ to be very fast, but it's very accident prone. There are lots of ways to handle arrays or lists in C++, but vector is both convenient and reasonably safe. So we're going to use vector. But vector isn't actually a type. Vector is something called a template. We're not going to learn too much about it yet, but it's kind of like a partial type. Now, in Python, if I have a list, I can put integers into a list, and then that same list I could append a string, and then a bool, and then a float, and then some object from some class. That's not true in C++. In C++, if I have an array or if I have a vector, all of the values I store have to have the same type. And that type that I'm allowed to store is actually part of the complete vector type. All you need to know about templates for now is that the word vector by itself is incomplete. It needs to be combined, the technical word is parameterized, by the type it's going to contain. And once it is, I use these angle brackets with the type here inside the angle brackets. Vector angle bracket int close angle bracket is a complete type. It is a class that allows me to store essentially a list. It is very, very much like a list from Python. And there's several different ways I could initialize. If I were to just put a semicolon here after the x would be an empty vector. And then I could possibly add to it. Here, though, I use a syntax that allows me to define essentially a list with 3 elements. So the actual type of this expression on the right is a little complicated, but in short, it's C++'s notation for a sequence of 3 values. And vector knows how to initialize itself from that, and x will then be a vector of size 3 that contains 1, 2, and 3. On the next line, I say y equals x. And remember, in C++, we get both value and reference semantics. If I were to write this in Python, both x and y would refer to the same list. Changing one would change both. Here, y is defined as a value, so it actually gets a full copy of x. If I were to write an ampersand right here where I've highlighted, y would be a reference, and then it would refer to the same vector as x. Again, this is the power of C++. You get to choose. There are a number of useful member functions on vector. I'll give 2 here and a lot more in the next slide. Dot size. This is the equivalent to Python's len function. The square brackets function exactly as they would in Python. But I also want to point out that you can create vectors of different types. You can store strings in a vector. And then I can initialize them here with the word hello and the word goodbye. But again, remember that C++ has types. A vector string and a vector int are different. And unless you tell the computer how, it's not obvious to the computer how to convert, or rather, it's not obvious to C++ how to convert one to the other. So if I try to assign x, which is a vector of integers, to z, which is a vector of strings, it simply fails to compile. Now, a few other useful functions. We already covered the first 2. Accessing an element. Note that this vi syntax, much like in Python, you can use it to access a value to read a value out, or you can use it to assign a value in as long as the vector is big enough. v.size returns the current size of the vector. How many elements does it contain? Pushback is the same as Python's append. Pushback means make the vector one larger and put x, the parameter, into the very last position. Front and back are convenience functions. v.front is like v square bracket 0. v.back is like v square bracket -1 in Python. Now, C++ doesn't have Python's shortcut for negative indices or Python's shortcut for slices. But you can still refer to the first and the last element this way, assuming they exist. Just one advanced tool that I want to mention, v.reserve. You won't have cause to use this anytime soon, but it's a little interesting in that if you know you're going to need room for 5 elements or 5,000 elements, you can say v.reserve 5,000, and it'll make sure there's space. It won't actually make the vector 5,000 elements long yet. There is a resize function that will do that. But reserve will make sure that it does any expensive memory operations that it might need to store 5,000 elements ahead of time. You can more or less forget the details of reserve for now. I'm just showing that there is some advanced functionality that if you care about making your programs run fast, there's a lot of techniques here in C++ for doing that. And now we're going to introduce a for loop. There are actually 2 ways you can write a for loop in C++. There's what we would call the traditional for loop, the C-style for loop, and the range for, or the for in, which is more like Python's for loop. For now, I'm only teaching you the second, the one that is a bit more like Python. Here, I define a vector of numbers, 1, 2, 3, 4, 5. And I use this syntax, the keyword for, and then in parentheses, the type of my iteration variable, the name of my iteration variable, colon. The colon here matches almost perfectly with Python's in keyword, for x in, or in Python this would read for I in numbers, colon, print I. In C++, we use colon instead of in. It must be wrapped in parentheses, and then instead, Once again, instead of indentation, we use curly braces. We can use a const ref as well. Instead of, so for this second for loop, I could have said for std string word in words, but instead we wrote const std string reference. And this is one of the first examples of why we might want to use a const ref instead of a value. In fact, this pattern using a const ref is the most common pattern I have seen for loops in C++. What's nice about it is we're doing two things. We're taking a reference instead of a copy. If I had done it like I did here, I would be copying strings one at a time out of this vector. Now, if those strings are very long, the longer the strings are, the more time it takes to copy them. So that is potentially a performance cost. By taking a reference, I never have to copy the string. I simply refer to the copy that's already there. So using a reference makes the code faster in this case. On the other hand, taking a reference would allow this code to accidentally modify those words. So I also include the keyword const. Together, this says, I want to refer to the words that are there. I don't want to create extra unnecessary copies of those strings, but I'm still promising to be a good citizen and not modify them as I go. All right. I want to talk about our next homework. This file isn't published yet, but it will be. I have a file for you to download. It contains, on the first line, a number n. That'll just be the number of lines following that on the file. All of those n other lines will describe a rectangle. The coordinates will be integers, and they will appear on the line x1. They won't appear with commas. It'll be x1, y1, x2, y2. So a rectangle, and these x1, y1, x2, y2 are the lower left and upper right-hand corners of the rectangles. They are parallel to the x and y axes, if you're worried about them being oriented funny. So I want you to do a few things with this data. First, in your code, I want you to implement a struct called rectangle. I want you to have a constructor or a stream operator. I haven't introduced what that is, but that is something you could look up, how to override the stream operator. But if I were you, I'd probably just stick with constructor for now. That's kind of a bonus if you want to do some reading on your own. I want you to do a constructor that will take in those four integers and, initialize your rectangle. And I want you to have a member function that tests for intersection. So that member function should take either, you could do it by a value to another rectangle, or better yet, a const reference to another rectangle. And that function should return true or false based on whether these two rectangles intersect. And I'm defining rectangles that intersect as two rectangles whose overlap has a non-zero area. Now, what you're trying to solve in this program is how many pairs of rectangles are there that intersect? So I'm giving you a large list of rectangles. Some of them will be on top of each other, some won't. For every combination of two rectangles that intersects, I want you to increment some counter by 1, and then print out that number at the end. And we can kind of check the numbers later when we're done. A few tips. First, remember that the rectangles have to overlap, not just touch. This is what I meant by saying the area of their intersection has to be greater than 0, not 0. Second, please be careful not to double count. A very easy mistake to make when writing this code would be to count an intersection between rectangles A and B, but then also to count the intersection between B and A. It's an easy mistake to make. If you do it, your count will be off by a factor of 2. And again, as I was saying, it would be best if you take your rectangle into your intersection function by const ref. Best of luck. Cheers.